This is EGR 101, Week 10, Units and Reverse Engineering. Good morning and welcome to EGR 101, Week 10, Units and Reverse Engineering. I'm going to deliver two lectures. This is part one, where we will cover units and reverse engineering, and then part two will focus on the homework. So hopefully we will get through this in two rather short videos. This is the first time I've done it this way, so we are all learning as we go. As you can see, this is my home office here. It is definitely not as neat as my office in the Grayhan building. So the truth is I keep Grayhan rather neat because I know I have visitors, but this one is a little bit messy. So we're going to go from here and I'll start narrating these PowerPoints. Email me with any questions. Thank you. So this is part one of our lecture series on units and reverse engineering. There will be a second part where I'll detail the homework and that will follow. So please look for that second lecture. So let's begin. So what we're going to do is we're going to detail a little bit more about units and dimensional homogeneity. Then I'm going to get into a brief discussion of reverse engineering, particularly how it fits into the design process. So dimensional homogeneity can be represented very simply by this equation here. I'm trying to find a length, and I have three other lengths that I add together to achieve that. Now let's suppose the length I'm trying to find is in meters. If A and B are also in meters but C is in inches, does that really make sense? I may get a numerical result, but I can't really say that that numerical result represents that total length in meters. In order to have a proper result, all three of those dimensions must be in the same units. Now I could have all three in meters, or I could have all three in inches and then convert the sum to meters, but in the end those three numbers have to be in the same dimensions. Here's another example. This comes from solid body mechanics. This particular example, if you think about the projectors that are in our classrooms, those projectors hang from the ceiling and there's a round bar that suspends them. That round bar acts like a spring, so it's possible to compute how much it deflects based on knowing the dimensions of the bar, knowing the mass or weight, I should say, of the projector, and also knowing a material property called modulus of elasticity. It's sometimes also called the elastic modulus or Young's modulus. It's basically a spring constant. Notice in this case that all of the units of measure that I have are in the metric system. So the question we have is, what are the units of measure of modulus of elasticity? So let's take a look at that. I'm going to take that equation there that lets me compute the deflection of the projector based upon the weight of the projector, the length of the support, and the cross-sectional area, and the Young's modulus. Now my deflection is in meters, my weight is going to be in newtons because it's a force, my length is in meters, and my cross-sectional area is in square meters. Similar to the pipes that we dealt with 4 homeworks ago. So the question is, what are the units of measure of the modulus of elasticity? Well, if I do a little rearranging down below, a little algebra, what I find is that the meters cancel top and bottom, and I'm left with newtons per meter squared. Those are the dimensions of modulus of elasticity. So let's look at another example. Now this is a little bit messy. This comes from the talk about Timoshenko, but modulus of elasticity was essential in Timoshenko's working of calculus to find an equation that we could use to design beams. He has a formula right here called stress equals strain times modulus of elasticity. Strain is really the deflection of something, the amount it stretches, if you will, divided by its initial length. Stress is the force on something divided by its cross-sectional area. So this really is F equals kx, same as for springs. Now what's important is what happens down here. When I worked this out for you to confirm that I had done the math right, because I wasn't completely sure I did this calculus correctly, I put in the various units of measure for these terms, and what I got is a result in newtons per square meter, or in this case, per pounds force per square inch. Those are the correct units for stress, so I knew that I did this right. So let's work through a problem here. We're making a gear. We're gearing up to do some calculations, so we're making a gear. We have some information concerning the production rate. We have some information about the amount of metal in pounds that goes into each gear, and we have a density. Now, what the plant has asked us to do, and I don't know why that they do it in this way, is they buy their metal in cubic feet. That's a weird way to buy metal, but we can't really argue with the plant. That's what they do. So the question is, how much metal do we need to buy for a week's worth of production? So let's take this information and see if we can compute that. So here's my answer. I want to ultimately get the volume of metal in cubic feet. This is what I know. It takes about a quarter pound mass of metal per gear. And I know I make 500 gears per hour, so if I multiply these two terms together, now I have the mass of metal per hour. But I know I have 18 hours of production in a day. Multiplying these two together gives me the mass of metal per day, and similarly this gives me the mass of metal per week. So now I've got the pounds mass of metal per week that I need. So my next question is, what do I do with this density term? Well, I have two choices. I can either multiply by density or divide. So let's step back and think a moment. What happens if I multiply by density? What units do I get? Well, I have pounds mass of metal times feet cubed per pounds mass, or I'm sorry, times pounds mass per feet cubed, because the density that I have is pounds mass per feet cubed. So that kind of tells me that if I did it that way, I'd end up with something with pounds mass squared per cubic feet, which is a nonsensical unit. I think I need to divide. So the units actually help me confirm that I need to invert that rather than to multiply by it. Let's switch gears. Very funny, isn't it? Let's switch gears to reverse engineering for a second. Why do I want to reverse engineer? And what do I mean by reverse engineering? Well, the best example I can give you is if I'm building that bridge across the Kentucky River, our Wildcat Engineering organization, I can look at other bridges across the river, or I can look at bridges up in Cincinnati or St. Louis or Louisville, or even go to Pittsburgh, and I can see how similar waterways were crossed. That's going to help me get a head start on my design. I'm going to see what other engineers considered. I'm going to see what worked and what didn't work. That's the big thing about this, what worked and what didn't work. Where does this fit into the design process? Well, generally people do their reverse engineering as part of their research. Some people call this past practice. Civil uses that term. Other people call this design patterns. That's very common in software or computer science. What I do is I take what I learned and define the problem where I get my good solid requirements and constraints. Knowing that, I look to see how other people have solved similar problems. That is where this fits in, and then that helps me start doing my detailed designing. Why do I reverse engineer? Well, the bottom line is it helps me to save time and money. It helps me to get a better design, to eliminate errors, and I'm more likely to get it right. Those are the big reasons that I do reverse engineering. So here's the steps to it. It's really kind of iterative, where I'm looking at what I'm doing, I'm observing how it works, I'm analyzing, and then I may actually even update my requirements and constraints based on what I learned. So that completes the first video. We're going to go ahead and do the second video, which is going to more detail the problem, the homework problem. If you have any questions or comments, please email me. I'll be online examining email for the duration of the rest of the semester. Okay, that's about it, and I'll see you soon with the other video. Bye for now.